So far, what we have done is we have done either limited number of factors or limited number of levels. So first we started with 2 levels, and we went to large number of factors. Then we went to large number of only 2 factors, but large number of levels. Now we are going to generalize everything. So we are going to do full factorial design with k factors with any number of levels. Okay, and this is basically the final chapter in experimental design. So this is the final chapter in experimental design. Again, we are going to do model and the analysis of a general design. Basically, I'm going to show you more from an example than formulas. And more importantly, in this chapter also, I'm going to discuss 3 methods which are very simple methods, and they are very powerful in that sense that they are very easy to explain to people and make sense. So you don't have to go into too much of statistics to explain to other people. So we'll talk about those 3 methods. So first, let's go into a general k-factor design. So if you had, instead of 2 factors, with 2 factors you just had one interaction, which was alpha, beta, and then the interaction was gamma. But if you have 3 factors, then you will have, basically 3 main effects. You will have overall mean, then you will have 3 main effects, and then you will have at least 4 interactions. You will have AB, AC, BC, and ABC. And out of that, basically AB, AC, BC are 2-factor interactions, and then ABC is a 3-factor interaction, and then you have errors. If you have k factors, then in general you will have k main effects and k and 2 out of k combinations, 2-factor interactions, and 3 out of k combinations for 3-factor interactions, and so on. So if you put k equal to 3 here, you get 2 out of 3 is factorial 3 divided by factorial 2 and factorial 1. That gives you 3. And for 3-factor interaction, you will similarly get 1. And similarly, you can put other values of k and see how many in 2-factor, 3-factor, 4-factor, and k-factor interactions you will get. And so this just becomes more and more complicated. And the analysis is very similar to what we saw before. The overall mean is equal to over mu, and then you subtract the mean along the first axis, and basically leaving the first axis but mean along all other axes, dot dot dot, and you get the parameter effects for that axis, and so on and so forth. And so it's much easier to explain this from an example, and I have this example here. So what we have here is 4 factors. Factor A is page replacement algorithm, which has 3 values: LRU, page replacement algorithm, FIFO, and random. Then second thing is the deck arrangement, which was group, frequency, and alpha. Problem program was small, medium, or large, and memory pages were 24p, 20p, and 16 pages. Okay. Now it doesn't really matter what these variables are, but you can see this is 3 by 3 by 3 by 3, total 81 experiments, 3⁴ design. So now, we're putting k equal to 3 in the previous slide. You can get how many interactions and so on and so forth, and we're going to calculate all of those. And so we did the 81 experiments, and here are the 81 numbers. Now let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9 times 3 times 3. So there are total 81 numbers, and you notice that the smallest value is, largest value is 23,134, the smallest value is 32, the ratio is too large, and so we went for the log transformation. And so we take the log of it first, and here are the 81 values, and now we can start doing the sums along each axis, and then calculate the alpha values, the effect values. So the main effects, for example, these are the main effects for A, 3 levels. First level is minus 0.16, second level is 0.02, third level is 0.14. For the factor D, so on for factor P and for factor M. And you can see that each of these rows add up to 0. Okay, the columns do not add up to 0 and will not need to be add up to 0 because they are not related. This just happens to be that all factors have 3 levels. Otherwise, some factors will have 2 levels, some will have 3 levels, some will have 4 levels, and so on and so forth. So there is no column-wise relationship. So now what we have done is total we have we have 4 times 3, 12 numbers. These are simply the main effects. Now we need 6 2-factor interactions, 4 3-factor interactions, and 1 4-factor interaction. 1 4-factor interaction obviously would be ADPM. Let's see, 6 2-factor interactions would be AD, AP, AM, DP, DM, and PM. So those would be 6 2-factor interactions, and 4 3-factor interactions would be ADP, ADM, DP, M, and so that is 4 right there, and then 1 4-factor ADPM. So basically all those can be calculated by doing the proper cells, and we did calculate them, and here are the values. These are the first order interactions, 6 of them, second order interactions, 4 of them, and the third order interaction, which is actually this is the 4th order interaction, second order, first order. Okay, so we have actually when we say first order, this is a 2-factor interaction. When we say second order, we have 3-factor interactions, and third order is the 4th-factor interaction. So there is a difference between the order and the number of factors. So anyway, and you can calculate how much percentage of variation each of them is explaining. It turns out the main effects explain 94% of the variation. The first order interaction explain another 5%. Second order interaction effect only 1%, and the third order interaction is very little. So for all practical purposes, you could possibly ignore second and third order interaction. Among the first order interaction, the only thing you really need to worry about is this one, DM. Everything else is very small. Okay, and so the model itself can be written down. So this is the DM interaction, as we said, D versus M. For 3 values of D, for 3 values of M, this is the DM interaction. And these are the errors, because what we did was for each experiment we calculated the value and subtracted that predicted value from the observation, and we get these errors, 81 errors, and we can calculate SSE, and we can also do normal quantile plot. You notice that there is one observation which is outside. Other than that, it's a good straight line. So first thing you have to do is to verify whether that outlier is an error in the experiment, or is it really the experiment value, and it was verified that that is okay, that is correct. So anyway, this is the final model, that the overall value is 2.90. Depending upon whether A is LRU or FIFO or RAND, you have to add these values, and depending upon whether the D is group, frequency, and alpha, you have to add one of these 3 values, and for P you have to add one of these 3 values, for M you have to add one of these 3 values, and then for DM you have to add respective values depending upon which value of D it is, 1, 2, 3, and which value of M it is, 1, 2, 3 on this side, and then plus minus 0.12. Anyway, so what we have done is we analyze the design, and this is a case study, so these are all real data, and what it is saying is that the best replacement algorithm is RAND. Actually, let me first see. I'm sorry, it's not the best, is not RAND. Best is LRUV, because this is a matrix. Pages swapped should be minimized, and so lower is better, and therefore minus 0.16 is better, best. So LRU, and then D is the group, and a small page size and 24 page memory. So now we move on to simple methods which are not so statistical, and we will explain these methods by simple examples. So the example that we are going to follow for the first method, which is called observation method, is that we have a schedule. We are designing a scheduler, and we have three classes of jobs: word processing, interactive data processing, and background data processing. There are 5 factors that we have not listed in here. It doesn't really matter, and we have used a 2⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ these are the 16 experiments right here, and these are the these are the values of the 5 factors which we did not list, but A, B, C, D, E. So these are the 5 factors, and these are 3 separate metrics, so they are not related. So this is the throughput on the word processing, throughput on the interactive jobs, and throughput on the batch jobs. And we are just going to analyze, let's say, only one right now for you, and that is throughput for the word processing. And generally you may not be interested so much in developing a model, but just trying to find out what is the best design, best scheduler design, so that you can implement that scheduler and not worry about any other alternative. So in this case, we are not so much interested in quantifying the effects. What we are interested in is really finding the best design. So all you have to do is go along this column and find the best. So you find the best is 28. The highest throughput comes out with 28. With 28, you have factor A is -1, factor B is 1, factor C is 1, factor D is -1, factor E is 1. And then you find, maybe next best. Next best is 27, and that also has some values. And then you compare these two, and you notice that A is in both cases -1, B in both cases is +1, C is not same, D is not same, E in both cases is 1. So you could make a conclusion that A equal to -1, B equal to +1, and E equal to +1 is somehow gives you high throughput, and C and D don't matter. Okay, so there are 2 ways to do this thing. One is that you could do the whole analysis. You are an analyst, and you know how to do the analysis, so you could do and quantify the effects and do all that. But later on, when you have to present it to people who don't know about this statistical method and normal distribution and so on and so forth, you could tell them as to how this particular combination is best by saying that, look here, A, this is how, basically the A -1, which actually stands for whatever the value A parameter A is, and then B equal to +1 and E equal to +1 give you the highest throughput. And that might be sufficient for those guys those people to understand this whole analysis. And you don't have to take them through all the mathematics that you went through yourself. Okay? So that's another thing, is basically if you ever, have to present an analysis, don't try to present all the complicated stuff to everybody, because your job is really to convince them of the final result and not show that you did very hard work. Okay? Hard work will show up, when you do this many times and people realize that, yeah, you understand what you're doing. All right, so that's the use of this. And second is, sometimes the list may be very long and you don't have time to or need to analyze it in that detail. In that case, you just do the simple method, and that gives you the answer that you need many times. The second method actually is an extension of the first method. In this, what we do is, we call ranking method. We just sort the column in the order that we want. So we sorted the whole design by this column TW. In this case, we are just trying to maximize the throughput for word processing workload. So you see this column has been sorted out, and all these columns have been accordingly rearranged values. And now what we do is, we try to see what are the common values on the top and what are the common values in the bottom. So I notice that A is on the top -1, and it remains -1 all the way up to here. and we start from the bottom, and we see that the A is +1 and it remains +1 all the way up to here. Then B remains +1, is on the top +1 and remains +1 up to here, and it is -1 but doesn't go very far. C is -1 at the bottom and goes up to here, and C is +1 at the top but doesn't go very far. D is -1, doesn't go very far, +1 on the bottom doesn't go very far. E is +1 on the top and goes to one more row, and E is +1 on the bottom and goes to 3 more rows. So now, having seen this, you can conclude that A equal to -1 is always better, because these are better experiments, higher values of throughput. So A equal to -1 is certainly better than A equal to +1. Okay. For B, we are not so sure, but if you have a choice, select B equal to 1. For C, we are not so sure, but if you have a choice, select C equal to -1. For D, doesn't really matter. For E, we are not so sure again. Okay. So that's the kind of thing that you would say. And if somebody just wanted one design, then obviously this is the best design, the top design, in which case you will use C equal to 1 and D equal to -1 as well. Although those will make very little difference in the overall, because between that C equal to -1 and D equal to +1, just the opposite, the difference is only 1. So you have to, with the ranking method, you not only get the best experiment, but you also get general trend of different factors. I must also point out that both these methods that we have talked about, they are not limited to 2 levels. You could have any number of levels here, and you could just put number 1, 2, 3, 4, 5, 6 in the matrix here, in the columns here, and then start. Basically, the experiments would be equally valid. Basically, the analysis can be done the same way. The third method, okay, actually these conclusions we have already gone through, so I'm going to skip this. The third method is range method. In the range method, what we do is for each combination, for each factor, we find out how much is the minimum and the maximum. So for replacement, now we are going back to the staging algorithm. Remember 81 experiments, and here is the response. Basically, the response goes from 2056 to 3781, and so the difference is 1725 between the maximum and the minimum. With deck arrangement, it goes from 1584 to 4326, so the difference is 2742. The range of basically of the observations is of the averages actually is 2742, and similarly for all these other, for memory sizes and so on and so forth. Now when you notice this, you see that the memory size has a big range, then comes the problem program, and then comes so on and so forth. So you can say that the most important, most influential factor is memory size. The next influential factor is problem program, and then the deck arrangement, and then the replacement algorithm. Because if you change the replacement algorithm, it is going to only change the performance by 1725, not more. But if you change the memory size, it will change the performance by that much. So this is basically another way to convince other people as to what your conclusions are, and so this is another method, or you can use it as to analyze as well when you have large number of experiments. That's basically the end of this chapter and the end of experimental design. What we have done in this chapter is that we have explained that if you have k factors with any number of levels, then you will have k main effects, and then you will have several 2-factor interactions, 3-factor interactions, and so on and so forth. And you can use statistical methods, or you can use one of these 3 informal methods. First method was observation method, in which you just take the best experiment and then try to use those values for your design. Second was ranking method, where you start out all the observations, and the third was range method, where you find the range of the largest versus to the smallest. Okay. What I have done here is just introduced you to the field of experimental design, and there are books which are as thick as my book, and they are just on experimental design. It's a very well established field, because while the computer scientists don't use experimental design that much, but medical scientists, agricultural scientists, they have to do a lot of experiments and they have to identify the effects very clearly. So they use it. So there are lots of books. So if you wanted to do a partial factorial design for general k factors with any number of levels, yes, those are all there. You will have to consult some more sophisticated book, and you can find the answer. Yes, so there is, for example, if you had a simple example would be 3 raised to k minus p design. Yes, and there are books which will tell you as to how exactly do 3 raised to k minus p design. All right, in this chapter there is a homework, and the homework is to analyze this particular data, which is 16 experiments, and you have to use the observation method first, and then you have to use the ranking method, both methods, and then submit the answer.